This is how to use our force toolkit to solve a non-equilibrium example where we're only using the variables. You should already be familiar with Newton's second law problems and our force toolkit. We will carry these out step by step. So in this particular example, we've got a crate that slides down an incline at an angle of theta above the horizontal. The coefficient of friction between the crate and the ramp surface is mu sub k. We need to find the acceleration of the crate. The other thing that we know is the mass is m. So our first step is to identify the object that's being accelerated, and that's obviously the crate. The second step is to determine what direction is positive. And for us, we're going to call the positive y direction this direction, because that corresponds with that direction there. That's a positive y. And we'll call that the positive x direction, because this will correspond with the positive x direction. Our third step is to draw the force diagram. So we've got the normal force pointing in this direction, where the surface is pushing up against the crate, and we've got the force of friction acting opposite the intended motion, because this crate is actually going to move in that direction. And then we also have the force due to gravity straight down. Our motion map shows that the velocity is increasing in the negative x direction, and so therefore our acceleration should also be pointing in the negative x direction. Part of step 3 is to also include our component diagram and to rotate if necessary. In this case, we do rotate. We rotate so that the normal force points straight upward. So we've taken this normal force and made it so that it is pointing upward. Now the frictional force points to the right, and our force due to gravity points down and to the left. And so now we've got two components for the force due to gravity. They are Fgy and Fgx. We're using the cosine for Fgy because it is adjacent to this angle, and the sine because it is opposite the angle. Then in step 4, before I go too much further, step 4 was to write out Newton's second law, and that's up there to the top left. Then step 5 is to write out Newton's second law in the horizontal and in the vertical. So in the vertical, we notice that we've got our normal force and we've got Fgy. According to Newton's second law, that it should equal the mass times acceleration in the vertical direction. But because there's no acceleration happening in the vertical, we know that this acceleration is 0, so therefore mass times the vertical acceleration is 0. We know that because if we look at our picture, it's not moving in the positive y direction or the negative y direction. In any vertical direction, it's not moving, so therefore the acceleration must be 0. So what we'll do is we'll substitute Fgy with mg cosine theta, and our equation would look like this. At this point, we're including our negative sign to show the direction. So our normal force is therefore mg cosine theta. Our next step is to look at the horizontal component. In the horizontal, we've got f sub k and Fgx. So we add them up according to Newton's second law in the horizontal. We add up Fk and Fgx, and we equal the mass times the horizontal acceleration. We know the value for Fgx because we showed it earlier. So Fgx is mg sine theta. So what that means now is we need to find the kinetic frictional force. Well, we've got an equation for the kinetic frictional force. It is this. This is the equation for the kinetic frictional force. We happen to know that equation, the equation for the kinetic frictional force, is mu sub k times the normal force. But fortunately for us, we already found the normal force above, and we can take that and plug it into there for our kinetic frictional force equation and find that we can substitute the value here into this equation to make the kinetic frictional force equal mu sub k mg cosine theta. Then what we'll do is we'll take this value for the frictional force, plug it back into this equation, and this equation will give us this new equation, where we now have F sub k here, so this is our frictional force, our Fgx, and that equals the mass times the horizontal acceleration. Now notice that there's a term of m in each part of this equation. They each cancel and become this value for the acceleration. And that's it.